In this video, we'll do an example that is similar to number 15 in the extra practice for 11.7 to 12.5, the extra practice for preparing for the second exam. So this problem says find the largest open interval where the function is increasing. So it's a lot like the previous one, but instead of being given a graph, we're given, let me change the color here. We're given an equation, f of x equals something. So f of x. And again, I won't do the exact same thing. I'll make up different numbers. Let's say 4x squared plus 2x to make something relatively simple. Um, the example in my math lab has fractions as coefficients, but you can always factor out 1/4, and then it's the same as this one essentially, with just different numbers. So if we want to look for where is a function increasing, if f is increasing, that corresponds directly with f prime being positive. Those two are directly connected. Okay, if the function is increasing, the derivative is positive, because remember, the derivative, this is slope, right? The derivative tells you the slope of the graph at a certain point. So if your graph looks like this, right, then this is just a reminder. Then right here, the graph is increasing. The slope is positive because the tangent line is positive. But at a point like, say, this one, right, the slope is negative because the tangent line is angled downward. The graph here is decreasing as you go left to right, of course. We read left to right. And here, f increases. And that correlates directly with the slope being positive or negative, right? So increasing means positive slope, so positive derivative. So I can take this function, find the derivative formula, and then I can look for, well, where is this positive? That will tell me where the graph is increasing. So I'll just use the power rule. So this is relatively easy. So this would be 8x plus 2. Now, and really I should call this step 1 because we're doing a multi-step process. So step 1, find the derivative. Step 2, I want to find out where is this derivative equal to 0, and that will help me discern chunks of the domain where the graph is increasing versus decreasing, because I'll look for where is the derivative positive versus negative, but I'm going to start with where is it 0. Really, there's actually a step that, since we're looking for critical numbers, I need to look for where is this undefined, and that is not a check mark, prime mark, it's more of an apostrophe, so where is this undefined? And 9 times out of 10, this won't get you anywhere, but in some cases it does, so you have to remember to check it every time, even though it usually it's not a waste of time. It's just, you know, you go to change the oil in your car, you have someone change the oil in your car, they check the wiper fluid just to see if it needs more. Usually it's not empty, but they just look at the fluids, right? You're just checking. So this is a check as you go along, which usually nothing happens, but you have to check anyway. Since this is a linear function, the domain is all real numbers, so there are no x values that you plug in for this function, the derivative, and you get no result. It doesn't work. That would only happen if you have like x in a denominator, where you might have a division by 0 with the right choice of x, or if you have x under a square root, so you would have a square root of a negative for the right choice of x. Those are basically the ways that's going to happen. There are other examples, but those are the most obvious ones. So in this case, no, there's no place where that happens. So we don't get any critical numbers that way. So now I'm going to look for where is the derivative 0. I need to solve this equation. So 0 equals 8x plus 2. And you'll notice I'm not calling this step 3. These two, looking for where the derivative is undefined and looking for where the derivative is 0, are really both step 2. It's two phases of step 2. So to solve this equation, I can subtract 2 on both sides. And then I can divide by 8. Of course, 2 over 8 is 1 over 4, so that reduces to negative 1/4. So, oops, equals x. So that means that the graph is neither increasing nor decreasing at negative 1/4 at x equals negative 1/4, because there the derivative is 0. So that's going to correspond to a local minimum or a local maximum, a high point or a low point in the graph, or not in this case, but potentially a corner in the graph, potentially, or an asymptote even. So step 3, I'm going to make a number line, and you don't have to draw it out this way, but I've broken something. What's happening? What am I doing wrong? Okay, I don't know what happened. I think maybe the software is just having trouble catching up with me. Okay, good enough. All right, so I'm going to mark -1/4. This is my critical number. Okay, mark with a little c so don't forget that that's what it is. Now, on this entire left chunk of the domain, for numbers less than -1/4, the graph is decreasing or increasing only. It can't switch between them. The critical numbers are precisely those places where the graph could switch from increasing to decreasing or vice versa. So this whole left chunk, there's only one possibility. The graph is either increasing or decreasing only for that whole chunk, but also the derivative is only positive or only negative for that whole chunk. So I need to pick one test point. And it doesn't matter what I pick. I should just pick something easy, like say -1 would be easy. And then over here on the right-hand side, I need to pick another test chunk. Again, it doesn't really matter what I pick. I could pick 15,000, and that will work. I just want to pick something that's convenient. I'll go with 0. That'll be easy to check. I'm going to check these in the derivative function. I need to find out where the derivative is positive, because again, I'm looking for the function f to be increasing, so I want to know where is the derivative positive. So I have to pick test points and look for a positive result from 8x plus 2. Okay, so go back down here, and I do f of -1, f prime of -1. Well, that's going to be 8 times -1 plus 2, which is -6 as a result. I don't really care that there's a 6, it's just that the result is negative is what I want. So the derivative is negative, so I'll mark a downward sloping line. That's not essential. You don't need to do that, but I find it helpful. Especially when you go on to use this for things like the first derivative test. It's convenient to get used to be in the habit of marking the increasing decreasing pattern with these up and down lines. So now I'll try at 0. So this is 8 times 0 plus 2, which is a total of 2, which is positive. Again, I don't care about the 2 exactly. I care about the 2 that does result as positive. If the result were plus 3 or plus 4 or plus 20, I don't care about the number amount, the quantity. I care about plus versus minus. So that tells me that the graph is increasing there. So this entire chunk, the graph is increasing. Remember, that is what I was looking for. Where is the graph increasing? And I basically found it. So my answer is the interval -1/4 to infinity. That's my answer. And on a multiple choice test, that would be one of the choices. Another choice might be the incorrect answer, the opposite, would be -infinity to -1/4. Okay. Another wrong answer choice might be like -infinity to infinity. Just if you were guessing, that looks reasonable. Possibly one of these numbers would get used. So maybe this 4 would be a good choice for a wrong answer. Maybe another wrong answer would be like -4 to infinity. And if you're guessing, if you really don't know how to work the problem, and you see this as a choice and you see this as a choice, you're kind of 50-50 between them. It's not necessarily clear. If you're guessing, then you don't know. So this last possibility is a somewhat likely wrong answer choice. If I were making one up, that's something I might put in there. Anyway, so that's that example. That is how you figure out where is the graph increasing or decreasing based upon a formula, f of x equals some formula, rather than the graph.